Okay, we return another integral from the UK integration B, sample problem number 2. We have the integral from 0 to infinity of sine x over x dx. Okay, this one's going to be another alternative method. I already did this one previously, and this method isn't even that different. I just feel like doing it a slightly different way, using Feynman's trick on it this time. So for Feynman's trick, what I'm going to want to do is I'm going to want to create something in order to kind of get rid of this x to make this easier to deal with. And so what I want to do here is I want to define a function and create another variable. We'll create t, and then we're going to want some expression with t in here that when I differentiate, it's going to allow me to eliminate this x. So what I'm going to want to try is, let's rewrite this, but what I'm going to do is multiply in another term, this e minus tx. And that's going to work nice because when you differentiate this term right here, a minus x is going to come out. We're not too worried about the minus sign, and that's going to give me the cancellation. So we're still going to have this other stuff here, but there's a few things I need to check before I just multiply this in so that I'm not changing it. So in order to not change it, what I can do is I can just set t equal to 0. So like our goal here can be f of 0, and that's going to work because if you just plug in a 0 for t here, this first piece is just 1, and so then it's going to be equivalent to our original problem. And then we're also going to want this integral to converge, but you can kind of see where our bounds are going to infinity. Well, when x is going to infinity, this first term is going to be going to 0 as long as our t is 0 or greater than 0. And one other thing we're going to want to need is we want another value of t where we can evaluate this so we can deal with the constant later on. We've already used 0, although we don't know what the 0 is yet, so that's our goal. But what we can do is, I mean, usually this isn't great notation, but what we can use is f when t is going to infinity. This is really going to be a limit, but I'm just kind of writing it that way because we know when t is going to infinity, the whole thing is going to be going to 0, and so we're going to know that value is 0, so we can use that later on. And then from here, all I want to do is we want to differentiate this, and we're differentiating with respect to t, so we're taking over here a derivative with respect to t. But for Feynman's trick, what we want to do is we want to differentiate inside the integral, so we'll do this in here, and we'll do it as a partial. We've got two variables, so we'll integrate here with respect to t. So now just going ahead with this, what's going to happen is first, this piece right here, so like we're differentiating all this, but this is just a constant with respect to t, so I'm just going to take this like outside, and we don't have to worry with that, so we'll just write that here as a constant. Then the derivative of this part with respect to t, that's just going to give me back e minus tx. Then chain rule on this part, and then what's going to come out is just minus x. So let's put it right here, minus x dx. But then the x's are going to cancel. That's what we want to get the simplification. I could take the minus sign out front here, and let's just rewrite it really quick. And now for this integral right here, we could do this by integration by parts, but I'm not going to because what you'll notice is this is actually the same thing as the Laplace transform of sine of x. So what we can do is for this just use a formula in order to get a value in terms of t for this. We have this formula for the Laplace transform of sine. We usually have it like sine a. We usually use t, but we'll say like the formula for the Laplace transform of sine ax. This is going to be the same thing as t squared plus a squared with a in the numerator. But with what we have right here, the coefficient on the x is just 1. So for this right here, this is actually just going to become 1 over t squared plus 1, or 1 squared. So using this, remembering this minus sign, our value for f prime of t, this is just going to be minus 1 over t squared plus 1. But now that we have a value for f prime of t, all I need to do is let's integrate on both sides, and we're integrating with respect to t here and here. But doing this is going to be an easy integral, right? This is going to be just minus arctan of t. But we're going to need the plus c on the end. And because we're integrating the derivative over here, this is going to become our f of t value. And what this is going to allow us to do is now we can come back, and this is why we created this value here, so we can have something where we can find this plus c value. So if we look what happens when f is going to infinity, really a limit, right? Then this is going to be, we evaluate arctan when it's going to infinity, that's going to be pi over 2 there, plus c, and we know this is going to be equal to 0. But in order for this to equal 0, we know that our c value just needs to be pi over 2. And so putting this back in here, we have our value, we have our f of t value, which is just going to be reordering it pi over 2 minus arctan of t. So this is going to give us our value of this thing that we set up originally, where we kind of created this e minus tx term that like isn't really there in our original problem. But the way we get back to our goal, the original problem, we want to find f of 0 when we just want to find when t equals 0. So we come down here, and if we just plug a 0 into this, we should be able to get our solution. So f of 0 is going to be pi over 2 minus arctan at 0. But arctan at 0 is just going to be 0. And so for my final solution on this, we just get pi over 2. Okay, there you have it. Really good one from the UK integration bee. Thanks everyone for watching. Have a good day.